Hey, when you look at your little bar of volume,
Yeah.
what are you peaking at?
Peaking?
Is it going all the way to 0?
When I when I smack.
Is the bar filling all the way up? Because you need.
Yeah. I
turn
can't.
your volume down.
All right, well, okay. Let me turn my volume down. Oh yeah, it's turned all the way up. Why is it doing that?
Oh boy.
All right. Hold up. How's that? That's probably a lot better.
That's so much better.
All right.
Welcome, everybody, to the Reference Frames Podcast, a physics podcast where we, myself and Will, try to take your favorite popular culture scenes and use them to teach you our favorite physics concepts. My name is Ian, playing the role of showrunner and hapless audience, and I'm joined by my good friend Will, aka
Will the physics man. Well, Ian.
We'll workshop that.
Yeah, we'll work. I don't have a title yet. But Ian, you said hapless. Did you know?
Oh boy.
Did you know?
Here we go.
Did you know that hapless and happy actually come from the word for like luck, like a word for luck? I think in Old English, like German vibe. So like
No.
Hapless makes sense because if you're hapless, you're unlucky. That's kind of what the word means. But happy less so. It originally meant a lucky person, and then eventually, I guess people who are lucky tend to be happy too. So, now that I wonder, I suppose happenstance and happen probably also come from the same root for like an occurrence of something. But I actually don't know about that. I assume that would make sense.
Doesn't matter. You've made a conjecture. You may be taken
Correction zone.
to the correction zone. For anyone who is unfamiliar with our podcast, what we do is Will read to us a narrative passage of some variety in order to activate our theater of the mind, bring us into a space where we can imagine something happening, and then together we will break down that physics. We will break down that scene and the physics that go alongside it in order to try to enrich our knowledge of the world around us.
Yeah.
Is that an accurate description of what we're going to do here?
I think so, yeah. I mean, just, usually, like, unlike last week, it would have been an anomaly. We plan on going for, like, TV shows or movies or books, or something, scenes from those kinds of things. Last week was a real world scenario because, Olympics. But this week we're going back to the world of cinema.
The world of cinema. But before we get there, where do we have to go first?
The correction zone. But I don't know, do we have any corrections from last week?
Do we have any corrections this week? I'm not sure.
I don't think we got corrected. I don't think we did.
Anyway, send us your corrections because we got to be able to fill out corrections corner more.
Yeah.
Or the errata
Yeah.
vertex.
We'll workshop that too.
We'll workshop that too. Okay, well, I guess that's all we have for corrections corner. So maybe bring us to the mind space.
In the latter half of the 21st century, humanity is on the brink of extinction. A series of blights have decimated more than half of the human population, as several staple food crops have entirely died out. In a last-ditch effort to save the human race, a team of scientists have been sent 10 billion light-years from Earth through a wormhole near Saturn. Bearing frozen embryos to reseed humanity on one of 3 potentially habitable worlds, they approach the first planet, one that is dangerously close to the event horizon of a supermassive black hole 100 million times the mass of the Sun. One of the crew maintains distance from the black hole in their main spacecraft, while the others go down to the planet to investigate, initially only planning for a brief stay to collect some data. The expedition is forced to remain on the planet for a number of hours, however, due to colossal tidal waves impeding their spacecraft's launch capabilities. By the time the expedition is able to flee the planet and return to their main craft, they find the crew member they left behind has aged 23 years in just the span of their expedition. This may seem on the surface to be a result of some fantastical curse or magic spell, but in fact every member of the expedition knew going in that any hour spent on the planet below would mean several years would pass both on Earth and on the main spacecraft. This is due not to anything supernatural, but rather entirely to the laws of physics as we currently understand them. End scene.
This little maneuver is going to cost us 17 years.
Ian, what do you think the concept is this week? There's a few little red herrings in there, so...
Are there some red herrings in there?
Well, you know...
We could be talking about mass. We could be talking about wormhole technology. We could be talking about waves and tides, even. Mm-hmm. Or we could be talking about time dilation.
Nice. You got it. Got it in one. Nice job.
Woo!
Yeah. Time dilation / gravitational time dilation, or general relativity.
And check this out. This is a new thing I'm going to add in, because someday when we make it big and we have sponsors, we would roll ads at some point in the middle of an episode. So if in the future you're listening to this podcast and we roll ads right here, know that we've made it big. Here we are. And we're back with time dilation.
Time dilation. Yeah. So first, a little preface, so you don't take me to the correction zone too hard next time. My field of expertise is not cosmology or astrophysics, so I'm not insanely well versed in general relativity or this kind of stuff. I've obviously studied it, and I know it fairly well, but I'm sure there are people who could listen that know much more than I do about this sort of topic. So just be aware. I might make a sloppy metaphor or maybe slightly misrepresent Albert Einstein. If so, that's fine. Send in your corrections. We'll read them next week, but just be aware that'll probably happen. With that said, though, I'll probably be glossing a lot of the nitty-gritty space-time curvature stuff and just not talking about that and talking more about what the effects of all that nitty-gritty space-time curvature stuff is, to keep it a bit more approachable. So hopefully I'll be avoiding some of the messy mires that I could fall into. So,
Caveat completed.
Physics
commence.
Yes, Einstein. Love you, buddy. In the early 20th century, 1905, 1915, he basically made these two different theories of relativity. So early on, he made his theory of special relativity, and then later on, and 10 years later, he generalized it to be a general relativity. So both of those different theories can explain a phenomenon called time dilation, which, as Ian, you pointed out, which is what we're seeing in this scene. So special relativity is nothing but the consequence of declaring the speed of light in a vacuum to be the exact same no matter how fast you're moving relative to anyone else. So anybody always sees the speed of light going the same speed, and that might seem odd if you think about it. But that truth leads to everything in special relativity. And in special relativity, if you are moving, period, full stop, relative to somebody else, they will see your time traveling slower. If you're moving, no matter how fast you are, the faster the more it happens, but if you're moving even a little bit compared to somebody else, they will see you experiencing less time, which is pretty weird. That's not what we're seeing in this scene, though. So in general relativity, which extends it to situations that allow for mass, which is pretty important. That's kind of everywhere. It also allows for accelerating reference frames. Hey, podcast.
Hey,
there we go.
It is. All right, wrap it up. We're done
Slipped
here.
It in, yeah. So general relativity allows for mass and for acceleration, which is also very important for describing the universe. So that in those situations, the closer you are to a mass, to any mass, the larger the mass, the more, and the closer the mass, the more. That will make time travel slower for you compared to somebody else looking at you. So somebody else will see you experiencing less time, and vice versa, where they'll see you experiencing more time. So that's what we're seeing in this scene. And just remember that the closer you are to the mass and the bigger the mass is, the faster someone else that's not as close, their clock will seem to be moving relative to you. It's pretty wiggy stuff. In this scene, what do we have? We have an expedition going very dangerously close to a huge mass, a black hole, a supermassive black hole, no less, which is said to be 100 million times the mass of the sun. So big mass, if you can imagine that. And you're getting basically as close as you can get. So if you go any closer, you're going to basically instantly die and get sucked in. No chance of escape. So they're basically doing as much as they can to cause as much time dilation as possible in the movie. Because I guess they like to have their crewmate get aged a lot. Yeah. So that's basically what's happening here.
So wait, let me break it down again. Mm-hmm. So the crewmate is staying in the ship, which is orbiting a big water planet.
Well, so it's actually further away than that. It's kind of they keep it farther away from the black hole on purpose because they don't want to spend. The guy actually on the ship wants to spend more time studying the black hole and stuff like that. So he stays further back because he knows it'll it'll his time will be zooming.
It'll take longer.
Yeah, he's prepared to spend a few more years, or like a few years studying stuff because he's a scientist.
Right. Okay. And they go in.
He stays away. Yeah, and they go in. Closer.
They get closer, and because they've gotten closer to that supermassive black hole, according to general relativity, they will experience time, or he will seem to experience time slower.
Yeah. So the guy that stays back will experience, according to the movie, the people on the planet in 1 hour for them, on Earth, for example, which has much less gravity going on than right next to a black hole, 7 years will pass for the people on Earth. So if they stayed there for an hour and immediately teleported back to Earth, everybody on Earth would be 7 years older minus 1 hour than they are.
Right.
So a little bit less for the guy, because he's not on Earth. He's still fairly close to a black hole, so probably like 5 years or something like that. But, same idea. So he experiences more time than they do, basically, by the time they come back.
Okay.
Yeah. Which is pretty cool.
Just wanted to break that down again, because that is weird.
Oh, yeah. Oh, it's very weird. And again, I'm trying to avoid all the space-time curvature, they go a further distance, therefore they experience less time. Like, I don't want to, the whole...
Yeah, and at some point it kind of only, like, you have to see it, kind of like see the equations to be like, oh yes, of course this must be this way. And that's no fun for a vocal medium.
Exactly. So that's basically what time dilation, gravitational time dilation is. If you go near a mass, the closer you get to the mass, no matter what mass it is, even if you get closer to somebody else or closer to the Earth or whatever, the sun, the stronger the gravitational field you're in, the slower your time will go. So, Ian.
Say that one more time.
Right. So if they were looking with like a telescope back at the guy on the big ship, he'd be zipping around his room, because in the span of a minute there, he's going through like months and months and months.
Right.
So as the minute passes, they'll see him zipping from back and forth, eating cereal, whatever he did on the spaceship. I don't know,
and if they looked at him,
or if he looked at them,
or if he looked at them, they would be going so slow.
Yeah, ridiculously slow. Yeah, there's actually some interesting things there with. If that's even possible. So like there's a book. So for this movie, they really wanted to make the science legit as they could. So they got an actual astrophysicist, Kip Thorne, to basically be the science advisor for the movie. And Christopher Nolan, the director, was like, "Hey man, I want an hour to be 7 years." And Kip Thorne is like, "I don't think that's possible. That feels like a huge amount of like time dilation." And he's like, "Make it happen, man. Don't do me dirty." And Kip Thorne's like, "All right, well, give me some time." Did some math, and he's like, "Okay, it's technically possible you can do this." So there's a few interesting things going on here. So black holes are effectively what happens. How you get a black hole is if you have a big, heavy star. At the end of its life cycle, it'll collapse. And if it's too light, it'll just explode outwards. But if it's heavy enough, it'll compress inwards and become a black hole. Or technically, they'll become a singularity, which is just when all the mass gets compressed into a very small point. And then they'll start sucking more stuff in and getting heavier and heavier and heavier. And these black holes have what's called a event horizon, which we talked about in the clip, right? So the event horizon is just the distance away from the mass, the singularity, at which even light can't escape, which is the most slippery devil you can imagine. So if light can't escape, literally nothing else can escape. And these black holes, these singularities, also can spin. They can have a rotational aspect to them. And the faster a black hole spins, this is what Kip Thorne had to do some finagling to get it to work. The faster the black hole spins, the smaller that event horizon becomes, due to some pretty hairy math. And in fact, if you spin there's a maximum speed. If you spin any faster than that, things start exploding mathematically, so it doesn't actually work. So there's like a speed limit for how fast these things can rotate. But as you approach that limit of how fast it can spin, the event horizon actually goes to half of what it was if it wasn't spinning at all. So it can get quite a lot smaller. The mass hasn't changed, but the limit at which the light can escape does. So that means he can put the planet closer to it if it's spinning really fast, because he doesn't want to be inside the event horizon. He needs to be outside. So if he just makes it spin really, really fast, he can put the planet right outside. Right. Like even closer, because the event horizon moves inwards. You can move it even closer to the center of the singularity, which makes time dilation even crazier. So like through a bunch of things like that, he basically was able to make it like, okay, technically it is possible to have a planet with just insane gravity going on where you get this huge 1 hour, 7 years scenario going on. So, Ian.
Jeez.
Yeah.
Are you about to ask me if I experience time dilation on a daily basis?
Yeah. Where do we see time dilation in the world today? I have 2 examples. If you don't have any, that's fine. I got the ability to think about it beforehand. So.
Oh boy.
All right. So the first one's a special relativity one, and it's less like actual like technology, and it's more like a fun thing you probably heard about. So have you ever heard of the twins paradox?
Probably, but I couldn't.
Will the Twins ever win the World Series?
Probably not.
No.
Let me tell you.
That's not it. Love you, TC. No. So
is that where you have a twin on Earth, you put a twin in a spaceship, and launch the spaceship to do the Ender's Game thing, spoiler alert.
Whoa.
And then the twin comes back.
Yeah. So exactly that. So if you have two identical twins, one's an astronaut, one isn't. The astronaut gets on a spaceship, flies off pretty close with the speed of light. That's kind of important. Flies very, very fast, right? Because the faster you go, remember, the slower your time goes. So it flies super fast to like Alpha Centauri or something, turns around and immediately flies all the way back, super fast. When they return home, they'll see that their twin who remained home has aged more than they have. If they travel further and faster, then they'll have aged perhaps way more than they have. So like one of them could even be dead of old age while the other one's still like 25 or something like that. And so you may have heard of that. It's kind of like the twins. Like, they're identical twins. How are they different?
It's because we launched them into space, dummy.
Dummy? Yeah.
I got one.
Okay.
But do you want to wrap up the twins paradox, or were you done with it?
No, I think it's fine. We can move on.
I believe it was the U.S. Navy put an alarm clock in in one of their very fast planes. And
it was an atomic clock, but yes.
It was an atomic clock?
An atomic
clock.
Alarm
clock with the little bells on it.
But yeah, you're right. They did. Keep going.
Is this one yours? Is this your second one?
No. This is not my second one.
Really?
My second one's a general relativity one.
Oh, and this is not, because we're moving at speeds approaching the speed of light, not gravity.
We're just moving fast.
We're
nowhere
fast.
near the speed of light. We're just moving.
No, we are not. That's an important point. 0.0001c. They put an atomic clock in, what was it, like an F-16 or something?
I don't remember. Some kind of plane.
They had 2 identical atomic clocks, I think. I haven't looked up the experiment in a while. Put one in a plane, right. Then they flew it fast for a long time, and then came back and compared the two clocks. And the atomic clock from the plane, because it moved faster, it had not gone as far as the second one.
In time, yes.
Haha. So while the first one, I don't think it was as severe as this. The first one may have gone an hour. The second one went, like 58 minutes?
Yeah, the one that was on the plane, yeah. Yeah, and that's why it wasn't an alarm clock, because alarm clocks have a precision to maybe a second or two, right? Atomic clocks have way more precision, because you're not going to get anywhere near the speed of light in an airplane. So it had to be really, really precise to be able to get like, 0.0000001%.
Fraction, yeah.
Very small variance. But they were different, and they, that's way of proving relativity. All right, so GPS relies on general relativity. Do you know that?
No.
Yeah.
What?
Mm-hmm. So GPS, as you're probably aware, it's like a network, I think as of 2020, 29 different satellites all orbiting the Earth pretty fast. So both relativities actually show up here, but the general relativity is the more important one. So just briefly, the way they determine positions, right, because that's the point, the global positioning system, right, is they send out signals that have timestamps associated with them, and your receiver receives these signals, and it gets them from it needs to be at least 4 different satellites so they can triangulate appropriately. But it receives all these signals with like the timestamps and also the identifier of which satellite and where the satellite is. And then from finding out how long ago each of those signals was sent, it finds out the distance to each of those satellites, right? And then it can triangulate where you are. That's basically how GPS works. So timekeeping is pretty important for GPS because it's all about how long these things took to get to you and also when they were sent, all that fun stuff. So GPS satellites have a lot of relativity going on with them. So they're moving very fast, moving around 14,000 kilometers per hour relative to the Earth's surface, which is where you are, right? Because it's all about the relative motion, hence relativity. So you're moving with the Earth's surface, they're moving 14,000 kilometers per hour faster than you, which means their clocks, which will run slower than your clock. And if you do the math, it ends up being around 7 microseconds less per day than I'll have, which isn't a huge difference, as you can probably guess. They're also, though, around 20,000 kilometers above the surface of the Earth, which means they're further from the mass of the Earth. So they're further away from the Earth, so their clocks run faster due to general relativity. So it sort of counteracts special relativity a bit.
Oh.
And it's quite a bit bigger of a difference. So it will count roughly 45 microseconds more. So 7 microseconds less, 45 microseconds more. Those might not sound like big differences, but in the end, that means they're off. They will lose about 38 microseconds each day and get, more and more off of our clocks down here. So if we didn't know about general relativity, we wouldn't know to correct for this, and we drift slowly away. But it's not even slowly, because 38 microseconds may not sound like a lot, but if you do the math again, and we'll have links for all this stuff we'll talk about the links at the end, but if you do the math a little bit, a 38 microsecond error in time, so even after 1 day of drifting, it'll be off there'll be an 11 kilometer error in your position.
Whoa.
Pretty significant.
That's quite a bit. You're not going to find your geocache.
No, not at all. So, and that's just after 1 day. So after 3 days, 3 times that. It's up by, 33 kilometers. So like, if we didn't know GR, if we didn't know general relativity, we weren't able to correct for that, GPS just would not function at all. In fact, let's say we set it up right. We didn't know general relativity, but we set it up right. It would be wrong and useless, entirely useless within 2 minutes.
Oh no!
Space.
What?
So it's a good thing we know relativity.
Thanks, Albert.
Yeah, thanks, Einstein. Good guy.
Wow.
Yeah. So that's my second one. That's a fun one.
That was a fun one. I liked that one.
Because we actually everyone uses GPS all the time. It's critical for daily life.
Like, Google Maps.
Mm-hmm. So that's what I got for a daily use case of relativity.
Do we need to wrap everything up in a nice bow?
Oh, yeah, probably. So you have this scene, right? They were not all surprised. They knew what was going to happen when they went to that planet. They knew they were going to spend more time there, or that he was going to spend way more time on the ship than they were. They just hoped it would only be a few minutes, or maybe an hour max. And the guy could, cryo freeze or something like that on the ship, and it wouldn't be a huge problem. They got waylaid for hours. So by the time they finally got off, and you get this really emotional scene where Cooper, played by Matthew McConaughey, is seeing this video, this feed of videos that have been saved up over the last 23 years that have been sent to him from his kids basically growing up, missing their entire childhoods, missing their early adulthoods, missing their marriages, But they knew because they knew relativity, right? They were astronauts, they were scientists, astrophysicists. But, you can't account for all giant tidal waves, turns out.
Don't let me leave, Murph.
Don't let me leave, Murph. But yeah, so relativity, it's critical if you're ever going on a journey to 100, was it 10 billion? How many billion light years away?
A lot, I guess, yeah.
Yeah, 10 billion light years.
Let's talk about some audience questions.
Yeah.
Audience question comes from our good friend at Cheese Puff himself.
At Cheese Puff.
At Cheese Puff.
I love cheese puffs.
What's the center of buoyancy? How is it different from the center of mass? So this is a follow-up to episode 2,
Nice.
The Secrets of the Fosbury Flop, aka Center of Mass. If you haven't listened to it, go give it a listen before you listen to the answer here. Otherwise, maybe you'll be confused. So, Will, please.
Yeah.
What's the center of buoyancy?
So we briefly talked about last week about, applications of center of mass, right? And I brought up ships and ballast and center of buoyancy and being important to be above the center of mass. Make sure I got that right. So the center of buoyancy, what is that? So the reason boats can float in the first place is they're being held up. They're being pushed up by a force. And in this case, it's the buoyant force. And the way you find a buoyant force is if you put a ship in the water, it displaces some of the water, right? It rides down into the water. Some of the water is pushed out of the way. And the way you calculate is actually pretty straightforward. Whatever the weight of that water you displace, so let's say you displace, 20 gallons of water with your little canoe. However much weight 20 gallons of water is, which I don't know what that weight is, but whatever that weight is, that is the force that's pushing you up. And so that can allow some things to float, like boats. Where that force is applied is at the center of buoyancy. And the center of buoyancy then if you just imagine looking like at the inside of that canoe, and you took all the water that should be there if the canoe wasn't there, the center of mass of all that water is the center of buoyancy. So it's the same basic idea as center of mass. It's just like a hypothetical, if the water had been there, where would its center of mass be? Hope that answers your question, Cheese Puff.
Thanks, Cheese Puff, for the question. For anyone else who has questions, you can tweet at us at Podcast Frames. Please, you should tweet us.
We have a
Your
Facebook.
questions, your corrections, your comments, your funny jokes, your fan art of me and Will
Yeah.
on a sailboat.
Questions about, tides or more relativity stuff or wormholes or black holes or whatever, shoot them our way. We'll do our best.
Are we going to the plug zone?
We're going to Plug Zone.
Toot toot! All aboard the train to the plug zone. Hi everybody, it's me, Ian, the plug zone man. Let's talk about how much you like our podcast and how you want to be involved to help. If you like this podcast, share it with your friends and your families and everyone in between. You can find us on all the major providers: Spotify, Apple. I even went for it and I got us on Google.
Whoa.
It was actually really easy.
Whoa. Well done. That's why I keep you around.
Another very helpful thing is if you would be so kind as to drop us a review on Apple Podcasts. We have technically we have 3 5-star reviews and one
1-star review. No?
And one review that has a message on it from our friends, Anna and Will. Thanks, Anna and Will, for leaving us a little review.
Nice. It's a good friend.
Much appreciated. I think that's the end of the plug zone. That's all I have, I think.
I think that's good. Actually, I'll leave us with a little note. It's kind of an interesting thing I learned while researching for this episode. Relativity is actually why gold is colored the way it is, rather than silvery.
Why?
Well, we won't get into it. I'm leaving it for a little nugget for if you want to
Oh,
think about
what?
it. Relativity is also why it's so non-reactive and thus resistant to both tarnishing and corrosion. So think about that.
Well, that's why you should always buy gold HDMI cables.
Heck yeah. So, and just to be, we'll leave some links. So there's a link to an excerpt from Kip Thorne's book that could be interesting to read if you want to learn about why he did what he did. An explanation of why black hole spin affects the gravity on the planet. An explanation about GPS. A brief explanation of the math behind the GPS. And also, I'll leave a link for that whole gold thing if you're interested. It's kind of cool.
Thanks, everyone, for joining us for another episode of Reference Frames Podcast. See you next time. Goodbye.
Farewell. I'll miss you.